in the last session 6. So we started Planck's quantum theory. Max Planck explained Planck's quantum theory to describe the nature of the black body. The black body is a perfect absorber and also a perfect emitter of radiant energy. It's a perfect absorber. That means the black body absorbs all the radiation, and being it is a perfect emitter, it transmits all radiations. So black body is the perfect absorber and also a perfect emitter of radiant energy. And we completed the graph plotted between intensity of the radiation energy and its wavelength. So we explained all the conclusion points of the graph. Now today let us commence with important postulates of Planck's quantum theory. Planck's quantum theory. Important postulates of Planck's quantum theory. Important points of Planck's quantum theory. According to Planck's quantum theory, the black body is, being it is a perfect emitter of radiant energy, the energy is radiated from the surface of the black body. Energy is radiated means the energy is produced on the surface of the black body, isn't it? So first, the energy is produced on the surface of black body due to the vibration of small particles like electrons. Energy is produced on the surface of the black body due to the vibration of small particles like electrons. Okay. Vibration of small particles like electrons. That is the point we can understand. Being it is a perfect emitter of radiant energy, that means energy has to be produced on the surface of the black body. That means the energy is producing on the surface of the black body due to the vibration of small particles like electrons. Good. Coming to the second point. The black body, the emission radiation from the surface of black body, the emitted radiation is not continuous. The emission radiation is not continuous but discontinuous in the form of small pockets. The emission radiation energy is not continuous like this. It's not continuous emission, it is a discontinuous emission. So each discrete pocket form energy is called, quanta, or you can call it as quantum. The discrete pocket form energy is called quanta or quantum energy. The emission radiation energy is not continuous but it is discontinuous in the form of small packets. Each packet form energy is called quanta or quantum. That is the second point according to Planck's quantum theory. First one, the energy is produced, the radiant energy is produced on the surface of the black body due to the vibration of small particles like electrons. Second point, the emitted radiation is not continuous but discontinuous in the form of small packets. That is, each discrete packet form energy is called quanta. Energy is called quanta. Is in the form of quanta or quantum. And this quantum energy is propagated in the form of wave. The quantum energy is propagated. The packet form quantum energy is propagated in the form of wave. Okay, that is, the discrete packet form energy is propagated in the form of wave. Okay. The emission radiation is not continuous but discontinuous. Each discrete discontinuous packet form energy is called quanta or quantum. The quantum energy is propagated in the form of wave. Okay. Next, coming to the third point. The emission radiation energy is directly proportional to its frequency, or E is equals to h nu. E is equals to h nu, where h is equals to Planck's constant. 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 Its value is 6.625 into 10 to the power minus 27 erg second, or it is equals to 6.625 into 10 to the power minus 34 joule second. That is Planck's constant value. So where E is equals to h nu, the equation is called Planck's quantum energy equation. E is equals to h nu is called Planck's quantum energy equation, and these values we should remember for the numericals, and sometimes it is also important directly they can ask you in the objective question. Okay, that is 6.625 into 10 to the power minus 34 joule second is the SI unit. Okay, right, we should remember that. Or the energy relations, that is E2 minus E1, that is equals to h nu, that represents, that is equals to delta E. The energy difference between two energy levels, that is delta E, is equals to h nu. That means when electron absorbs the quantum energy and emits quantum energy, always takes place in the form of h nu, that is quantas. Delta E is equals to E2 minus E1, that is equals to h nu. Okay, that means when electron transition takes place between two energy levels, say it is first orbit n is equals to 1, and it is second orbit n is equals to 2, and energy of the electron in the first orbit is E1 and second orbit is E2. When electron transition takes place between two energy levels, the absorption energy or emission energy, delta E is equals to E2 minus E1, that always equal to h nu. Yes. So these are few salient features of Planck's quantum theory. Okay, once again let us see the Planck's quantum theory. That is, Planck's quantum theory explains black body radiation. Black body is a perfect absorber and also a perfect emitter of radiant energy. So Planck's quantum theory explains the nature of the black body, right? The salient features of the Planck's quantum theory as follows. The energy is produced on the surface of the black body due to the vibration of small particles like electrons. The emitted radiation from the surface of the black body is not continuous. It is discontinuous. The discrete packet form energy is called quanta or quantum. The quantum energy is always propagated in the form of wave. The emitted radiation energy is directly proportional to its frequency. E is equals to h nu. Okay, where h is equals to Planck's constant. H is equals to Planck's constant. The values are given like this. This E is equals to h nu is called Planck's quantum energy equation. So, when electron transition takes place between two energy levels, the change in energy delta E is equals to E2 minus E1, that is equals to h nu. Okay, and what are the other relations of the energy? Let us see. For the objective window, let us consider like this. As we know that E is equals to h nu and nu is equals to c by lambda, and that is E is equals to hc by lambda. So first one is related with energy with frequency, second equation energy with wavelength, equations here, that is E is equals to h nu, frequency relation, energy frequency relation, and so let us see the energy ratio of the two radiations with its frequency relation is equals to directly proportional to frequency, nu 1 by nu 2. This is one relation we can understand. And second, where that is E is equals to hc by lambda, that is inversely proportional to the wavelength of the light. So that we can say energy relation with wavelength. So we can consider E1 by E2 is equals to lambda 2 by lambda 1. So all this comes under objective window. Important formulas to be noted down. Okay, that is wavelength relation, it is frequency relation. And next let us see wave number relation. Wave number E is equals to hc nu bar, hc nu bar, that is E1 by E2 is equals to nu bar 1 by nu bar 2, that is wave number relation. And for n number of photons, so that is E is equals to nh nu, okay. So that n represents for number of photons or number of quantas, okay. These are all some important relations. And another one, delta E is equals to, that means delta E is equals to, that is E2 minus E1, that is equals to h nu. So we can calculate energy difference between the two energy levels with its quanta frequency. Yes. So these are some important relations from Planck's quantum theory. Okay, these are some relations of Planck's quantum theory. Now, so after this Planck's quantum theory, Einstein's generalization. Einstein's generalization, or we can say Einstein's approach. Einstein's generalization of Planck's quantum theory or Einstein's approach. According to Einstein's approach, yes, the radiation energy is produced on the surface of the black body due to the vibration of small particles like electrons. Done. Next, the emitted radiation is not continuous, but it is discontinuous. The discrete packet form energy, he called it as photon. He called it as photon energy. Is called photon energy. So When electron absorbs photon energy, the electron jumps from lower energy level to higher energy level. When electron absorbs photon energy, the electron jumps from lower energy level to higher energy level. The process is called excitation. When a normal ground state electron absorbs photon energy, it absorbs h nu, absorbs photon energy, the electron jumps from lower energy level to higher energy level. The process is called excitation. When electron jumps from higher energy level to lower energy level, it emits photon energy. The process is called de-excitation. During excitation, the electron absorbs photon energy. During de-excitation, electron emits photon energy. So absorption and emission photons always takes place in the form of light only. Okay, so therefore the electron transition between two energy levels, that is delta E, is equals to E2 minus E1, that is equals to photons, h nu. Okay, so that is always electron, that is absorption energy and emission energy always takes place in the form of photons. 1 photon, 2 photon, 3 photon, like that. Okay, it cannot be in fractional. So this is about Einstein's generalization. Here he clearly explains that is when electron absorbing some photon energy, the electron jumps from lower energy level to higher energy level. The process is excitation. And when electron jumps from higher energy level to lower energy level, it emits photon energy. So that is called a de-excitation process. So which was not explained by Planck's quantum theory. Simply he said that the radiation energy is produced on the surface of the black body due to the vibration. He mentioned only the vibration. So now that vibration was clearly explained by Einstein's, that is excitation and de-excitation process. Okay. During this excitation and de-excitation process, so the electrons emits radiation in the form of photons, that is h nu. Okay, that is about the detailed explanation of Planck's quantum theory. Okay, that is Planck's quantum theory. Okay, now this is completely, we have a numerical, very important concepts, that is formulas are there in this. So that is energy relation with frequency, energy relation with wavelength, and energy relation with wave number, and energy relation with number of photons. Here you can use E is equals to n h nu. E is equals to n h c by lambda we can use, or we can also use E is equals to n hc nu bar. So the important relations we can identify for all the objective examinations, very important numerical concepts from this Planck's quantum theory. Okay, energy with frequency, energy with wavelength, energy with wave number, and energy with the number of photons, including the number of photons. Okay, so that is done. Okay, now the next coming to the photoelectric effect. That is, after completing this Einstein generalization of Planck's quantum theory, Einstein explains photoelectric effect. That is Einstein's photoelectric effect. Einstein's photoelectric effect. Einstein's photoelectric effect Einstein's photoelectric effect. What is the concept of Einstein's photoelectric effect? See, the surface of a metal has its own number of atoms on the surface of the metal, and every metal atom has its electron. Every surface atom has its own electron. So this is surface on the metal, and we are observing, so a particular atom is possessing electron. Okay, now certain frequency photon light, or you can say certain wavelength photon light, that is called incident light. When certain photon light, photon means it is nothing but light having its energy is in the form of photons. So certain photon light falls on the metal surface. When certain photon light falls on the metal surface, the surface electron absorbs. The surface electron absorbs. The surface electron absorbs. It is incident energy. So E, energy of the photon light. So that is E is equals to h nu. We know that this is incident light. It speaks about incident light, that is incident photon. So now, when certain wavelength, or you can say certain frequency photon light or certain energy photon light falls on the metal surface, the surface electron on the surface of the metal, the electron on the surface of the metal is not free. It is binded to the surface by some attractive forces. Okay, so now the surface electron absorbs some part of the photon energy, So this is energy of the incident light falling on the metal surface. Now this surface electron is absorbing some part of the photon energy. Okay, some part of the photon energy. Then the electron is relieved from all the surface forces. Then the electron is ejected from the metal surface. So this electron is called photoelectron. Okay, the electron, by absorbing photon energy, ejected from the metal surface, therefore the electron is called photoelectron. Then the other part of the energy, the remaining energy, is released as kinetic energy of the photoelectron. So for example, so it completely speaks about incident light, and it speaks about absorbed light. It is absorbed light. Okay, it is incident, it is absorbed. As we know that E naught is equals to h nu naught. Okay, because E and E make a difference. It is incident light, energy of the incident light, frequency of the incident light. Similarly, we can also give relation with wavelength. E is equals to hc by lambda. So it is a relation between lambda and energy. It is frequency and energy. It speaks about complete incident light, the light which is falling on the metal surface. Okay, now E naught is equals to h nu naught. Okay, it speaks about complete absorbed photon light. Okay, so that E naught is equals to hc by lambda naught. E naught is equals to hc by lambda naught. It completely speaks about absorbed energy. Okay, it is incident energy, it is absorbed energy, right? So once again, what is E naught? The amount of energy absorbed by the electron to eject from the metal surface is called threshold energy. This energy is called threshold energy. Threshold energy. What is that threshold energy? The amount of energy absorbed by the electron to eject from the metal surface is called threshold energy, or it is also called work function. It is also called work function. Okay, so this is denoted as E naught or W. So this can be represented as E naught, or it can also be represented as W. Okay, that is represents about threshold energy or work function. Okay, completely, that is, it speaks about E naught is equals to, we can say, threshold energy or work function. What is nu naught? Nu naught is equals to, that is, E naught is equals to threshold energy or work function, whereas nu naught is equals to threshold frequency. Threshold frequency. This is threshold energy or work function. Work function. Whereas H is the Planck's constant, we know that. H is equals to Planck's constant. And whereas C is the velocity of light. Velocity of light. And whereas lambda naught is threshold wavelength. Threshold wavelength. Threshold wavelength. So it speaks about complete absorbed energy. It speaks about complete absorbed energy. This speaks completely about incident energy. So the electron is ejected from the metal surface. The remaining energy is released as kinetic energy. Once the definition of Einstein's photoelectric effect. When a certain photon light falls on the metal surface, the surface electron absorbs some part of the photon energy, then the electron get excited, that is ejected from the metal surface. The other part of the energy is released as kinetic energy of photoelectron. For example, if the energy of the incident light, for example, say it is 100 joules. 100 joules energy is falling on the metal surface. The surface electron is absorbing some part of this. Say for example, 40 joules energy is absorbing. Okay, why it is absorbing some energy? To relieve from the attractive force, because it is binded to the surface. It's not free, it is binded to the surface. So this much of energy is absorbed to get relieved from all the forces, attractive forces. Then the free electron is ejected from the metal surface. The remaining energy, the remaining balance energy, that is the other part of energy, that is 100 minus 40, that is 60. The other part of the energy is released as kinetic energy of the ejected electron, that is photoelectron. Okay, now that is total energy is equals to threshold energy plus kinetic energy. Or we can say total energy is equals to, or total energy is equals to, E naught is also called work function, W. It can also be represented as W plus kinetic energy. These are the basic fundamental, okay, that we can understand easily. So E is equals to H nu, we know that H nu, or you can say we can calculate kinetic energy. Kinetic energy is equals to, that is total energy minus threshold energy, that is E minus E naught. So then we can calculate kinetic energy like this, okay, or kinetic energy is equals to E is nothing but h nu. So this is h nu and this is h nu naught. So therefore let us take h common and nu minus nu naught. Okay, these are the basic fundamentals of photoelectric effect, Einstein's photoelectric effect. So mostly kinetic energy frequently they are asking. So therefore the kinetic energy is equals to h as the Planck's constant, and nu is the frequency of the incident light, and nu naught is the frequency of the absorbed light, that is threshold frequency. Okay, so once again let us define what is threshold frequency. The frequency of the light absorbed to eject from the surface of the electron is called the frequency of the light required to eject the electron from the metal surface is called threshold frequency. Similarly, threshold wavelength, the wavelength of the light absorbed, the wavelength of the light absorbed by the electron to eject from the metal surface is called threshold wavelength. Okay, these are some important aspects of Einstein's photoelectric effect. Okay, in the next coming session let us see the numericals of Planck's quantum theory and photoelectric effect.